Right now, every cell in your body is alive because of a razor-thin balance of pressure, temperature, and chemistry that exists nowhere else in our solar system. Step off this planet unprotected, and physics will kill you. Not in some abstract future sense, in seconds. Scientists have calculated what would happen to an unshielded human body on every world orbiting our sun, and the results are terrifying. Mercury would boil and freeze you in the same day. Venus would crush you before you could scream. Neptune would shatter your frozen body with supersonic winds. Each planet has its own signature method of destruction, and not one of them is quick enough to be painless. This is what the solar system really looks like when you remove the spacesuit. Not to be dramatic, but if you want to hear how every planet would destroy you, and why Earth is the only reason you are reading this, hit that like button and subscribe. Now, settle in and get yourself comfortable. Let's begin. You have never thought about what keeps you alive. Not really. You understand it in the abstract. You need air. You need water. You need food. You need warmth. But you have never sat quietly and considered the specific physical parameters that separate your living body from a dead one. You have never examined the exact numbers that your biology demands from its environment every single second. Those numbers are precise. They are non-negotiable. And they define a survival envelope so narrow that crossing any single boundary by even a modest margin triggers a cascade of failure that ends in death. This is not a metaphor. This is measurement. And every measurement begins with a baseline. Earth is the baseline. The atmospheric pressure at sea level on Earth measures approximately 101.3 kilopascals. That number represents the cumulative weight of every molecule of gas in a vertical column, stretching from the ground to the uppermost boundary of the atmosphere, a column roughly 100 kilometers tall, pressing down on every square centimeter of surface. You are buried at the bottom of an ocean of air, and that ocean exerts force. Roughly 1 kilogram of pressure on every square centimeter of your skin. Your entire body sustains a load of approximately 17,000 kilograms, roughly 17 metric tons of atmospheric weight. You do not feel it because your internal pressure matches it precisely. Your cells, your blood vessels, your lungs, your sinuses, every fluid-filled and gas-filled cavity in your body is pressurized from within to exactly counterbalance the atmosphere pressing from without. This equilibrium is so seamless that you forget it exists. It is the single most important physical condition sustaining your life, and you have never once been conscious of it. Remove that external pressure, and the equilibrium shatters. The gases dissolved in your blood, nitrogen, oxygen, carbon dioxide, come out of solution, forming bubbles inside your veins and tissues. Your lungs, accustomed to inflating against atmospheric resistance, overexpand. Fluid in your soft tissues begins to vaporize, not because the temperature has changed, but because the boiling point of water drops as pressure decreases. At pressures below approximately 6.3 kilopascals, water boils at 37 degrees Celsius human body temperature. Your blood and tissue fluids begin transitioning from liquid to gas while still inside your body. This process is called ebulism, and it is one of the fastest ways physics can dismantle a living organism. The oxygen content of the atmosphere defines the second critical parameter. Earth's atmosphere consists of approximately 78% nitrogen, 21% oxygen, 0.9% argon, and trace quantities of carbon dioxide, neon, helium, and other gases. That 21% oxygen concentration is not a convenience. It is a hard constraint imposed by 3.5 billion years of evolutionary calibration. Below 16% oxygen at sea level pressure, cognitive impairment begins. Below 10%, consciousness fails. Below 6%, death follows within minutes. But the relationship runs in the other direction too. Above 50% oxygen for prolonged periods, the gas becomes toxic. Oxygen radicals attack lung tissue, cause inflammation, and eventually destroy the alveolar membranes responsible for gas exchange. The breathable window is narrow, roughly 14 to 50% at standard pressure, and Earth's atmosphere sits comfortably in the middle of that range. The partial pressure of oxygen matters as much as the percentage. At sea level, the partial pressure of oxygen is approximately 21 kilopascals. This is the driving force that pushes oxygen molecules across the alveolar membranes in your lungs and into your bloodstream. Reduce total atmospheric pressure, even if the oxygen percentage stays the same and the partial pressure drops proportionally. At the summit of Everest, where atmospheric pressure is roughly 1/3 of sea level, the partial pressure of oxygen falls to about 7 kilopascals. Climbers in this zone experience severe impairment. Most require supplemental oxygen. Without it, the death zone above 8,000 meters claims lives every year, not because oxygen is absent, but because the pressure is too low to force enough of it into the blood. Temperature constitutes the third boundary. The average surface temperature of Earth is approximately 15 degrees Celsius, though local variation spans from roughly -90 degrees in Antarctica to about 57 degrees in the hottest deserts. The human body maintains a core temperature of approximately 37 degrees Celsius through thermoregulation, an intricate system of metabolic heat generation, vasodilation, vasoconstriction, perspiration, and shivering that adjusts continuously to environmental conditions. This system is effective but limited. If core temperature drops below 35 degrees, hypothermia begins. Below 32 degrees, the heart becomes unstable. Below 28 degrees, ventricular fibrillation becomes likely. Death follows shortly after. In the opposite direction, core temperatures above 40 degrees trigger heat stroke. Above 42 degrees, cellular proteins begin denaturing, losing the three-dimensional folding that allows them to function. Enzymes fail. Metabolic pathways shut down. Organ systems collapse in sequence. The thermal corridor within which human biochemistry operates spans barely 14 degrees. 14 degrees between survival and systemic failure. Earth's climate keeps the vast majority of its surface within this range for most of the year. No other planet does. Radiation protection forms the fourth parameter, and it is one most people never consider. Earth generates a magnetic field through the motion of liquid iron in its outer core, a self-sustaining dynamo that projects a magnetosphere, extending tens of thousands of kilometers into space. This invisible structure deflects the solar wind, a relentless stream of charged particles, primarily protons and electrons emitted by the sun, at velocities ranging from 300 to 800 kilometers per second. Without the magnetosphere, those particles would bombard the upper atmosphere directly, gradually stripping away the ozone layer and allowing ultraviolet radiation to reach the surface at biologically destructive intensities. The ozone layer itself, concentrated in the stratosphere at altitudes between roughly 15 and 35 kilometers, absorbs the majority of ultraviolet B and virtually all ultraviolet C radiation from the sun. Ultraviolet C is energetic enough to break DNA strands directly. Ultraviolet B causes mutations that lead to skin cancer. Earth's dual-shield magnetosphere plus ozone reduces surface ultraviolet exposure to levels that biology can tolerate. Remove either shield, and the surface becomes inhospitable to complex life within a geologically short time frame. Gravity closes the list. Earth's surface gravitational acceleration measures approximately 9.8 meters per second squared. This value dictates the structural engineering of every organism that has ever lived on this planet. Human bones possess the density and mineral composition needed to bear loads at 1 g. Human muscles generate the force required to move a skeleton at 1 g. The cardiovascular system pumps blood against 1 g of gravitational resistance, maintaining adequate cerebral perfusion while you stand upright. Reduce gravity significantly and the body begins to decay. Bones lose calcium, muscles atrophy, fluid pools in the upper body, and vision degrades as intracranial pressure shifts. Increase gravity beyond roughly 3 to 4 g for sustained periods, and the heart cannot maintain blood flow to the brain. Consciousness fades. Circulatory failure follows. Earth's gravity is not merely comfortable, it is structural. Human physiology is load-bearing architecture calibrated to this specific gravitational environment. 5 parameters: pressure, oxygen, temperature, radiation shielding, gravity. Each one defines a threshold. Cross any single threshold and biological function begins to degrade. Cross 2 and degradation accelerates. Cross all 5 simultaneously and you are not on Earth anymore. You are on every other planet in the solar system. Hold those 5 parameters in your mind. They are the ruler against which every world that follows will be measured. Every planet will be tested against this checklist. Does it provide the pressure, the oxygen, the temperature, the shielding, the gravity? The answer, in every case except one, is no. The only variation is how violently each planet delivers that verdict. Mercury is the closest planet to the Sun. It orbits at a mean distance of approximately 57.9 million kilometers, just 39% of Earth's orbital radius. If you could stand on its surface during perihelion, the Sun would appear nearly 3 times larger in the sky than it does from Earth, and its radiant intensity would be approximately 6.7 times greater. Mercury is a small world, 4,879 kilometers in diameter, barely larger than Earth's moon, and smaller than Jupiter's moon Ganymede or Saturn's moon Titan. Its mass is a mere 5.5% of Earth's, producing a surface gravity of approximately 3.7 meters per second squared, roughly 38% of what you feel on Earth. You would weigh about a third of your normal weight. That gravitational lightness is one of exactly 2 gentle things about Mercury. The other is the silence. Because Mercury has no atmosphere to carry sound, the planet is perfectly, absolutely quiet. It is quiet because there is nothing to make noise with. Mercury possesses no atmosphere in any meaningful sense. What exists is an exosphere, a diffuse scattering of atoms so sparse that individual particles almost never collide with one another. Sodium, oxygen, hydrogen, helium, and potassium atoms hover above the surface, blasted free from rocks by solar wind bombardment and micrometeorite impacts. The total density of this exosphere is so low that it constitutes a better vacuum than anything achievable in a terrestrial laboratory. The surface pressure on Mercury is approximately 1/10 billionth of a pascal. Earth's sea level pressure is 101,300 pascals. The ratio between these two values spans approximately 15 orders of magnitude. For every unit of pressure your body experiences right now, Mercury provides less than 1/10 quadrillionth of that. This is not a thin atmosphere. This is the void of space with a rocky floor. The vacuum is what kills you first on Mercury. Not the heat, not the cold, not the radiation. The vacuum. Everything else is secondary, because the vacuum operates faster than any thermal or radiological process can. The physiology of vacuum exposure has been studied with uncomfortable thoroughness. NASA, the United States Air Force, and various military research programs conducted experiments throughout the 1950s and 60s to understand what happens to biological organisms, including, in a few cases, human subjects when ambient pressure drops to near zero. The data is consistent and unambiguous. In the first 1 to 2 seconds of vacuum exposure, the air in your lungs begins expanding against a chest wall that no longer has external pressure to resist it. If you reflexively hold your breath, which is the instinctive human response to sudden environmental threat, the expanding gas will rupture alveolar tissue, forcing air bubbles directly into the pulmonary vasculature. These bubbles enter the bloodstream as arterial gas embolisms, which can travel to the brain and cause immediate stroke-like symptoms. Trained astronauts and high-altitude pilots are taught to exhale forcefully during any rapid decompression event for precisely this reason. Holding your breath in a vacuum is not brave, it is suicidal. Within 3 to 5 seconds, the reduced external pressure allows dissolved gases in blood and interstitial fluids to begin forming bubbles, the onset of ebulism. This is distinct from decompression sickness, which occurs when nitrogen comes out of solution slowly during ascent from depth. Ebulism is faster, more violent, and more globally destructive. At pressures below the Armstrong limit of 6.3 kilopascals, water transitions to vapor at body temperature. The fluids in your mouth, your eyes, and your exposed mucous membranes begin to boil. Subcutaneous tissues swell as water vapor expands beneath the skin. Hands and arms puff up to roughly twice their normal volume. The swelling is painful, but not immediately fatal. The skin is elastic enough to contain the expansion without rupturing, but the circulatory system is now pumping blood that contains gas bubbles, and those bubbles obstruct flow through capillary beds throughout the body. Between 5 and 10 seconds, the oxygen remaining in your bloodstream is consumed by metabolic processes that continue regardless of whether new oxygen is being supplied. Arterial oxygen partial pressure plummets. The brain, which consumes roughly 20% of the body's total oxygen supply, despite comprising only 2% of body mass, is exquisitely sensitive to this decline. At approximately 10 to 15 seconds, deoxygenated blood reaches the cerebral vasculature. Consciousness fails. This timeline is not theoretical. In 1966, a technician at NASA's Manned Spacecraft Center in Houston experienced accidental exposure to near-vacuum conditions when his spacesuit suffered a pressure failure inside a vacuum chamber. His last conscious recollection was the sensation of saliva boiling on his tongue. He lost consciousness after approximately 14 seconds. Chamber operators repressurized the environment within roughly 25 to 30 seconds, and the technician survived with no permanent injury. Had repressurization been delayed by another 30 to 60 seconds, the outcome would have been death. After unconsciousness, the body continues to deteriorate. The heart keeps beating. For a time, cardiac muscle can function briefly without conscious neural input, but it pumps increasingly compromised blood through tissues that are swelling, deoxygenated, and progressively damaged by embolism. Cardiovascular collapse typically occurs between 45 and 90 seconds after initial exposure. By 90 seconds, the damage is almost certainly irreversible. By 120 seconds, survival is effectively impossible even with immediate medical intervention. On Mercury, there is no vacuum chamber operator standing by. There is no repressurization switch. The nearest breathable atmosphere is approximately 77 million kilometers away on the planet you left behind. Your survival time on Mercury from the moment of unprotected exposure is approximately 60 to 90 seconds. 120 seconds at the theoretical maximum for a physiologically exceptional individual with a robust cardiovascular system. Most humans would be dead in under 1 minute. That is the primary cause of death: vacuum. The absence of pressure that your body was engineered to expect. But Mercury layers additional brutality on top of this baseline lethality, and the thermal environment deserves attention even though it operates too slowly to outrace the vacuum. Mercury rotates with extraordinary sluggishness. One sidereal day, the time for one complete rotation relative to the stars, lasts approximately 58.6 Earth days. But because Mercury also orbits the Sun, the solar day, the time between one sunrise and the next at a given location, stretches to approximately 176 Earth days. This means each hemisphere faces the Sun continuously for roughly 88 Earth days before rotating into darkness for another 88 days. The thermal consequences of this prolonged exposure and withdrawal are extreme beyond anything found on any other terrestrial world. On the day side, surface temperatures reach approximately 430 degrees Celsius. This exceeds the melting point of lead by over 100 degrees. It exceeds the melting point of zinc by about 10 degrees. Tin melts at 232 degrees, roughly half the Mercurian dayside temperature. If you placed a block of lead, a bar of zinc, and a tin soldier on Mercury's sun-facing surface, all three would melt into puddles. The rock beneath your feet would be radiating heat intense enough to ignite wood, melt solder, and soften aluminium. On the night side, the temperature crashes to approximately negative 180 degrees Celsius. This is colder than the lowest temperature ever recorded on Earth's surface, negative 89.2 degrees Celsius at Vostok Station in Antarctica by nearly 100 degrees. At negative 180 degrees, Carbon dioxide freezes into dry ice. Ethanol, which remains liquid down to -114 degrees, would solidify. The thermal swing between Mercury's dayside and nightside exceeds 610 degrees Celsius. No other planet in the solar system exhibits a thermal range even remotely comparable. The reason for these extremes is the same reason the vacuum kills you: the absence of atmosphere. On Earth, the atmosphere functions as a massive thermal buffer. It transports heat from warm regions to cold regions through convection. It absorbs outgoing infrared radiation and re-emits it back toward the surface, the mechanism that keeps nights warmer than they would otherwise be. It reflects incoming sunlight, moderating daytime heating. It stores thermal energy in water vapor and distributes it globally through weather systems. Mercury has none of these mechanisms. The surface is naked, exposed directly to solar radiation during the day, and radiating freely into the 3 Kelvin background of deep space at night. There is nothing between the rock and the cosmos. Nothing to smooth the extremes. Nothing to moderate the brutal arithmetic of a world baking in direct sunlight for 3 months and then freezing in absolute darkness for 3 more. If you arrived on Mercury's dayside, the radiant heat from the surface would cause severe thermal injury before your feet touched the ground. At 430 degrees Celsius, the surface emits infrared radiation at an intensity that would cause second-degree burns on exposed skin within seconds of proximity, even without direct contact. Physical contact with the surface would produce instantaneous 4th-degree burns, destruction extending through the dermis into subcutaneous tissue, muscle, and potentially bone. Clothing would ignite on contact. The rubber soles of ordinary shoes would melt. Even the metallic components of a wristwatch would become hot enough to brand the skin beneath. If you arrived on the night side, the outcome reverses direction but remains equally destructive. At -180 degrees, exposed tissue would undergo rapid frostbite. Skin cells would crystallize within seconds. Blood flow to extremities would cease as vasoconstriction attempted to preserve core temperature. Hypothermia would accelerate as the body radiated heat into an environment that offered nothing in return. But neither thermal scenario matters for your survival timeline. Burns kill over minutes to hours. Hypothermia kills over minutes to hours. Vacuum kills in under 2 minutes. You would be unconscious from embolism and anoxia before the thermal environment had a chance to inflict its full damage. The heat or cold would savage your body. Certainly there would be visible thermal injury by the time cardiovascular collapse occurred, but the cause of death would be recorded as vacuum exposure, not thermal trauma. Temperature is the supporting actor. Vacuum is the executioner. Mercury's radiation environment adds one final layer to the hostility, though it too operates on timescales irrelevant to immediate survival. The solar flux at Mercury's orbit is approximately 6.7 times the intensity received at Earth. Without an atmosphere to absorb ultraviolet radiation, and without a global magnetic field to deflect charged solar particles, Mercury does possess a weak magnetic field, roughly 1% the strength of Earth's, but it provides minimal shielding. The surface receives a continuous barrage of high-energy protons, ultraviolet photons, and X-ray emissions. Over weeks to months, this radiation would cause catastrophic DNA damage, acute radiation syndrome, and almost certain death from systemic organ failure. But over 60 to 90 seconds, the radiation dose is negligible. It never gets the opportunity to contribute to the outcome. There is one final detail about Mercury worth noting, because it carries a bitter irony. Data from NASA's Messenger spacecraft, which orbited Mercury from 2011 to 2015, confirmed the presence of water ice deposits in permanently shadowed craters near Mercury's north and south poles. Due to Mercury's negligible axial tilt approximately 0.03 degrees, compared to Earth's 23.4, certain crater floors near the poles never receive direct sunlight. Temperatures in these permanently shadowed regions remain below -170 degrees Celsius year-round, cold enough to preserve water ice for billions of years. The planet closest to the Sun, bathed in radiation intense enough to sterilize stone, harbours ice in its shadows. This ice is not a refuge. It exists in hard vacuum, at cryogenic temperatures, in craters that never see the sun. No human could reach it, touch it, or use it. It is a geological curiosity locked behind every lethal parameter Mercury possesses: vacuum, temperature, and radiation all at once. The water is there. It might as well be on another planet. Here is your Mercury summary. The dominant lethal factor is vacuum exposure. Consciousness is lost within 10 to 15 seconds due to cerebral anoxia. Death from cardiovascular collapse and embolism follows within 60 to 90 seconds. Thermal extremes cause significant tissue damage, but operate too slowly to outpace the vacuum. Radiation is irrelevant on this timescale. Mercury kills you the way open space kills you, by removing the atmospheric cocoon that 4 billion years of evolution assumed would always be there. The planet offers no atmosphere, no pressure, no oxygen, no thermal regulation, and no radiation shielding. It scores 0 on all 5 survival parameters. The surface of Mercury is simply the floor of the vacuum. You are not dying on a world. You are dying in space that happens to have rocks underfoot. Everything that kills you on Mercury traces back to a single absence. No atmosphere. Pressure, oxygen, temperature moderation, radiation shielding, all of them depend on having an atmospheric envelope, and Mercury has none. 101.3 kilopascals of pressure stand between you and this fate. On Earth, you receive every one of those kilopascals. On Mercury, you receive none. And Mercury, for all its extremes, is the gentle introduction. The next planet inward toward the Sun does not kill you through absence. It kills you through overwhelming, crushing, incinerating presence. What comes next makes vacuum exposure seem almost peaceful. Venus should have been Earth's twin. The two planets formed from the same primordial disk of gas and dust, at roughly the same distance from the young Sun, from roughly the same raw materials. Their diameters differ by only about 650 kilometers. Their masses differ by less than 20%. Their surface gravities are nearly identical. If you could strip away the atmosphere of Venus and the atmosphere of Earth and place the two bare rocky spheres side by side, you would struggle to tell them apart. They are siblings born in the same neighborhood, built from the same blueprint, shaped by the same gravitational forces during the solar system's earliest epochs. And yet one became a world of oceans, oxygen, and life. The other became the most lethal surface environment of any rocky planet orbiting our Sun. Venus is not dangerous the way Mercury is dangerous. Mercury threatens you with absence, no air, no pressure, no thermal regulation. Mercury is a void. Venus is the opposite. Venus threatens you with presence, too much atmosphere, too much pressure, too much heat, too much chemistry. Everything about Venus is an excess that crushes, incinerates, and corrodes. If Mercury is death by deprivation, Venus is death by overdose. Venus orbits the Sun at a mean distance of approximately 108.2 million kilometers, about 72% of Earth's orbital radius. It is the second planet from the Sun and the closest planetary neighbor to Earth, approaching within roughly 38 million kilometers at its nearest pass. From Earth, Venus is the brightest natural object in the sky after the Sun and Moon. Ancient civilizations worshipped it. Roman mythology named it after the goddess of love. Galileo observed its phases through a telescope in 1610. For centuries, astronomers imagined Venus as a tropical paradise hidden beneath its brilliant white clouds, a lush, warm world where exotic life might flourish under perpetual overcast skies. They could not have been more catastrophically wrong. The atmosphere of Venus is a weapon. It consists of approximately 96.5% carbon dioxide and 3.5% nitrogen, with trace quantities of sulfur dioxide, argon, water vapor, carbon monoxide, helium, and neon. This composition alone is lethal. Carbon dioxide becomes toxic to humans at concentrations above roughly 5%, causing rapid respiratory acidosis as the blood's pH drops and the body's acid-base balance collapses. At 96.5%, every breath would flood the bloodstream with carbonic acid. Confusion, unconsciousness, and respiratory arrest would follow within seconds. But the composition is almost irrelevant because the mass of the atmosphere makes it unreachable. The atmosphere of Venus contains approximately 93 times more gas than Earth's atmosphere. This enormous blanket of carbon dioxide presses down on the Venusian surface with a force of approximately 9.3 megapascals, 92 times the pressure at Earth's sea level. To build intuition for what 92 atmospheres means, consider how pressure accumulates underwater on Earth. For every 10 meters of depth beneath the ocean surface, ambient pressure increases by approximately 1 atmosphere. At 100 meters, you experience roughly 11 atmospheres, 10 from the water column plus 1 from the air above. At this depth, the human body can still function briefly with specialized breathing equipment, though nitrogen narcosis impairs cognition and decompression sickness threatens any diver who ascends too quickly. At 300 meters, roughly 31 atmospheres, only the most extreme saturation divers operate, housed inside pressurized chambers and breathing exotic helium-oxygen mixtures. At 500 meters, most military submarine hulls begin approaching their crush limits. At 700 meters, roughly 71 atmospheres, even advanced deep-diving submarines risk catastrophic structural failure. The surface of Venus sits at a pressure equivalent to roughly 920 meters below the ocean, deeper than the operational limit of virtually every crewed vessel ever built by human engineering. The human body is not a submarine. The ribcage is a semi-rigid structure of bone and cartilage designed to expand and contract against 1 atmosphere of external pressure. The intercostal muscles, the small muscles between your ribs, generate the force that inflates your lungs during inhalation. That force is calibrated to overcome 1 atmosphere of resistance. At 92 atmospheres, the external pressure on the chest wall exceeds the structural capacity of these muscles by a factor that makes resistance impossible. The force pressing inward on the human thorax at Venusian surface pressure would be roughly equivalent to placing 75 to 100 tons of weight on a person's chest. The ribs would fracture. The sternum would depress inward. The lungs would collapse completely, not deflate, collapse, driven flat by external force far beyond what any biological tissue can resist. The compression would not stop at the chest. At 92 atmospheres, every gas-filled cavity in the body would be crushed. The sinuses, air-filled pockets in the skull bones would implode. The middle ear cavities would rupture. The intestines, which contain gas from digestive processes, would compress violently. Even blood, which is largely incompressible as a liquid, would experience changes in gas solubility. Dissolved gases would be forced into tighter solution, and any existing microbubbles would collapse under the pressure. The entire body would be subjected to a compressive force comparable to an industrial hydraulic press. This destruction would occur within approximately 1 second, perhaps less. The transition from 1 atmosphere to 92 atmospheres would not be gradual. You would arrive at the surface instantaneously, and the full weight of the Venusian atmosphere would bear down on your body without any period of acclimatization. There is no pressure gradient to descend through slowly, as there would be in an ocean. You are simply there, and 92 atmospheres are simply upon you. Chest collapse, organ compression, and circulatory failure would constitute a single, near-instantaneous event. If the pressure were somehow survivable, which it is not, the temperature would finish you independently. The surface of Venus maintains a nearly uniform temperature of approximately 465 degrees Celsius. This figure requires contextualization because human intuition has no framework for temperatures to this extreme outside of industrial settings. An ordinary kitchen oven maxes out at roughly 260 degrees Celsius. A self-cleaning oven cycle reaches approximately 480 degrees close to Venus's surface temperature. A wood-fired pizza oven operates at roughly 400 to 500 degrees. The surface of Venus is approximately as hot as the inside of a pizza oven during peak operation. Now imagine being inside that oven. Not near it. Inside it. with 92 times normal atmospheric pressure compressing you simultaneously. At 465 degrees, human tissue does not simply burn. The biochemistry undergoes pyrolysis, the thermal decomposition of organic molecules into simpler compounds. Proteins denature and fragment. Lipids in cell membranes break down. Water, which constitutes roughly 60% of body mass, would not boil. The extreme pressure keeps water liquid at temperatures far above its normal boiling point, but it would become superheated, functioning as an internal thermal conductor that accelerates tissue destruction from within. Skin would char. Fat beneath the skin would render. Muscle tissue would undergo coagulation necrosis, stiffening and contracting as proteins solidify. This is the chemistry of cremation, occurring not in a purpose-built furnace but in the open air of a planet's surface. The uniform distribution of this heat is one of Venus's most remarkable and terrifying features. Unlike Mercury, where temperature swings by over 600 degrees between day and night, Venus maintains its 465 degrees with almost no variation. Dayside, nightside, equator, poles, the temperature is essentially the same everywhere on the surface. This uniformity results from the extraordinary efficiency of Venus's atmospheric heat distribution. The dense atmosphere acts as a massive thermal reservoir, absorbing solar energy on the dayside and circulating it globally through convective currents. Additionally, the greenhouse effect on Venus is the most powerful of any planet in the solar system. Carbon dioxide is transparent to incoming visible sunlight, but absorbs outgoing infrared radiation heat emitted by the surface. The thick carbon dioxide atmosphere traps this outgoing energy with extraordinary efficiency, creating a thermal feedback loop that has elevated surface temperatures to levels far exceeding what proximity to the Sun alone would produce. Venus is actually farther from the Sun than Mercury, yet its surface is over 300 degrees hotter. The atmosphere is the difference. Mercury's lack of atmosphere lets heat escape freely. Venus's crushing atmosphere holds heat captive. Above the surface, the cloud layers of Venus add a final chemical insult. Venusian clouds extend from approximately 48 to 68 kilometers above the surface and consist primarily of sulfuric acid droplets at concentrations estimated between 75 and 98%. Concentrated sulfuric acid is one of the most corrosive substances in industrial chemistry. It dehydrates organic tissue on contact, reacting exothermically with water in cells to produce intense localized heating and chemical burns that penetrate deeply into tissue. On Earth, concentrated sulfuric acid is handled only with full protective equipment, chemical-resistant gloves, face shields, and body coverage. The sulfuric acid clouds do not directly affect survival at the surface. Because the droplets evaporate during descent, the heat is too intense for liquid sulfuric acid to survive the trip to ground level. However, the lower atmosphere retains sulfur dioxide, a pungent and toxic gas that reacts with moisture and mucous membranes to form sulfurous acid. Traces of hydrochloric and hydrofluoric acid have also been detected. In any other context, these corrosive agents would constitute a serious chemical hazard. On Venus, they are an afterthought. You are already dead from pressure before the first acid molecule contacts your skin. The Soviet Venera program demonstrated exactly how hostile Venus's surface is, even to hardened machinery. Between 1970 and 1985, the Soviet Union landed a series of increasingly robust probes on Venus's surface. Each was a triumph of engineering reinforced titanium alloy pressure vessels designed to withstand 92 atmospheres, pre-cooled with circulated refrigerant to delay the onset of thermal failure. Venera 7, in 1970, became the first human-made object to transmit data from another planet's surface. It survived approximately 23 minutes before succumbing. Venera 9, in 1975, returned the first photographs of the Venusian surface and lasted roughly 53 minutes. The longest surviving lander, Venera 13 in 1982, transmitted data for approximately 127 minutes, just over 2 hours, before the heat overwhelmed its electronics and the mission ended. These were machines specifically engineered for the conditions, reinforced, pre-cooled, insulated, built from materials selected for thermal and chemical resistance. A titanium-armored spacecraft, the product of some of the most ambitious planetary engineering of the 20th century, survived 2 hours. An unprotected human body, soft, water-filled, pressure-equilibrated to 1 atmosphere, structurally dependent on a skeleton that fractures under load, would last approximately 1 second. The disparity between engineered durability and biological fragility has never been more starkly illustrated. Your survival time on Venus, approximately 1 second. The pressure kills first, the heat kills simultaneously. The toxic atmosphere and corrosive chemistry never get their turn. Venus destroys a human body the way a hydraulic press destroys a watermelon through instantaneous, overwhelming mechanical force, accompanied by thermal destruction so intense it constitutes incineration. Now stop, reset, return to Earth. Remember what normal feels like. The gentle pressure of air against your skin, the ease with which your lungs inflate and deflate, the warmth of sunlight that heats without burning, the sky that shields without crushing, the atmosphere that contains exactly the right molecules in exactly the right proportions at exactly the right pressure. This is the only place in the inner solar system where breathing is not a death sentence. Carry that awareness forward, because from here we travel outward, past Earth's orbit, past the comfortable distances, into the cold margins where the sun begins to lose its grip and the atmosphere thins to almost nothing. Mars is the most psychologically treacherous planet in the solar system. Every other world announces its hostility honestly. Mercury is visibly barren, a cratered wasteland with no sky. Venus hides behind impenetrable clouds that scream danger even from orbit. Jupiter and Saturn are obviously alien vast spheres of swirling gas with no visible surface. But Mars deceives. Mars looks like somewhere you could go. The photographs sent back by the Spirit, Opportunity, Curiosity, and Perseverance rovers show rust-coloured rocks and fine-grained soil stretching toward a horizon that curves gently under a butterscotch sky. There are hills, valleys, sand dunes, and boulder fields. The terrain resembles the deserts of Utah or the volcanic plains of Iceland. Dried river channels carved by ancient water snake across the landscape. Layered sedimentary formations suggest lakes that persisted for millions of years. Polar ice caps gleam white at the North and South Poles, water ice mixed with frozen carbon dioxide, growing and shrinking with the Martian seasons. The visual language of Mars is Earth-like enough to trick the brain into a fatal miscalculation. Your visual cortex processes the images and concludes, this is a place where I could walk, where I could explore, where I could survive. That conclusion is wrong. Mars is almost as deadly as Mercury, and it kills through the same fundamental mechanism, atmospheric failure, but it wraps that lethality in a disguise of almost habitability that makes the truth more disturbing. Mars orbits the Sun at a mean distance of approximately 227.9 million kilometers, roughly 1.5 times Earth's orbital distance. It is a small world, with a diameter of approximately 6,779 kilometers, slightly more than half Earth's diameter. Its mass is about 10.7% of Earth's. Surface gravity measures approximately 3.72 meters per second squared, 38% of Earth's, coincidentally the same as Mercury's. On Mars, your body would feel light. Walking would require less effort, jumping would carry you higher. The reduced gravity would feel liberating, even exhilarating, and it would make no difference whatsoever to your survival. The Martian atmosphere is the problem. It exists, which already places Mars ahead of Mercury, but it is so thin as to be functionally useless for sustaining human life. The average surface pressure on Mars is approximately 636 pascals. Earth's sea level pressure is 101,325 pascals. Mars provides roughly 0.63% of Earth's atmospheric pressure, less than 1%. If Earth's atmosphere were a swimming pool, Mars's atmosphere would be the thin film of water left behind after you wiped the tiles with a damp cloth. This pressure is critical because it falls far below the Armstrong limit, the threshold, at approximately 6.3 kilopascals, where water boils at human body temperature. The Armstrong limit represents a hard physiological boundary. Below this pressure, the partial pressure of water vapor at 37 degrees Celsius exceeds the total ambient atmospheric pressure. This means exposed body fluids, saliva on the tongue, moisture on the eyes, water in the mucous membranes of the respiratory tract begin transitioning from liquid to vapor at normal body temperature. The blood itself does not boil in the dramatic, cinematic sense. It remains largely contained within blood vessels, and the skin provides enough mechanical resistance to prevent explosive vaporization. But dissolved gases come out of solution aggressively. Tissues swell with water vapor. Ebulism begins the same process that kills in hard vacuum, initiated here by a pressure that is technically above zero, but functionally equivalent to nothing. The entire surface of Mars lies below the Armstrong limit. Every square meter of terrain, from the summit of Olympus Mons, the tallest volcano in the solar system, rising approximately 21.9 kilometers above the surrounding plains, to the floor of Hellas Planitia, the deepest impact basin, sits at a pressure that would cause bodily fluids to boil at body temperature. There is no altitude on Mars where the pressure is safe. There is no valley deep enough, no crater sheltered enough, no location on the entire planet where an unprotected human would not experience ebulism. The atmospheric composition offers no consolation. Martian air consists of approximately 95.32% carbon dioxide, 2.7% nitrogen, 1.6% argon, and trace amounts of oxygen at approximately 0.13%, carbon monoxide, and water vapor. The oxygen content is roughly 1/600th of Earth's. Even if the pressure were adequate, which it is not, the gas mixture would cause fatal carbon dioxide toxicity within breaths. Each inhalation would deliver nearly pure carbon dioxide into the lungs, driving blood pH downward in a spiral of respiratory acidosis. But again, the pressure failure preempts the toxicity. Your lungs cannot function at 600 pascals regardless of what gas fills them. The sequence of physiological failure on Mars would closely resemble hard vacuum exposure with minor variations. The decompression sequence that played out on Mercury would repeat here, with only minor variations. Moisture on the eyes and skin would vaporize within the first seconds. Vision would blur as the corneal surface distorted and dried. The sclera is tough enough to prevent rupture, but not to maintain optical function. Tears would boil on your cheeks. Dissolved gases in the blood would form microbubbles, occluding capillary beds and impairing circulation throughout the body. Based on accounts from altitude-related decompression incidents, the conscious experience would include intense joint pain and a sensation of pressure building behind the eyes. Then, between 10 and 15 seconds, cerebral oxygen depletion would end consciousness. The brain consumes its available oxygen reserve with extraordinary speed once fresh supply ceases. After consciousness fails, the body continues its downward trajectory. The heart beats for another 30 to 60 seconds, pumping blood that is increasingly gas-filled and deoxygenated. Tissues swell. Circulation ceases. Cardiovascular collapse occurs at roughly 60 to 90 seconds after initial exposure. Survival time on Mars, approximately 60 to 90 seconds, functionally identical to Mercury. The clock runs on the same mechanism, oxygen deprivation and ebulism, and arrives at the same endpoint at nearly the same moment. But Mars layers additional threats that Mercury does not possess, and though these threats operate too slowly to outpace the atmospheric failure, they deserve examination because they reveal how comprehensively Mars rejects biological life despite its hospitable appearance. Temperature on Mars averages approximately -60 degrees Celsius globally. The range extends from roughly -140 degrees at the winter poles to occasional daytime highs near 20 degrees Celsius at equatorial latitudes during southern summer. That equatorial warmth sounds survivable. and for a few hours during a Martian afternoon, the air temperature at certain locations does fall within the range a human could tolerate. But the thin atmosphere carries almost no thermal energy. Air at 600 pascals of pressure contains so few molecules per unit volume that it cannot transfer meaningful heat to or from the human body through convection. On Earth, a warm breeze carries substantial thermal energy because each cubic meter of air contains roughly 1.2 kilograms of gas. On Mars, a cubic meter of atmospheric gas weighs roughly 15 grams, about 1% of Earth's air density. A warm Martian afternoon would feel like standing in a vacuum, with a thermometer that reads 20 degrees. The number is reassuring, but the thermal environment is not. Instead, the body would lose heat primarily through radiation infrared emission from the skin into the cold Martian environment. This radiative cooling is rapid and unmitigated by atmospheric insulation. Even at the warmest equatorial sites, an exposed human body would begin cooling immediately, with extremities reaching hypothermic temperatures within minutes. In the more typical regions of Mars, where temperatures sit between -40 and -80 degrees, radiative and conductive heat loss would drive hypothermia far faster. But once again, the timeline is academic. You are unconscious in 15 seconds and dead in 90. Hypothermia kills over hours. Mars gives you a minute and a half. Then there is radiation. Mars lacks a global magnetic field. It possessed 1 billion years ago. Paleomagnetic signatures in the ancient southern crust confirm this. But the planet's core cooled, the internal dynamo ceased, and the magnetosphere collapsed. Without magnetic shielding, the solar wind impinges directly on the upper atmosphere, slowly stripping it away over geological time. This is likely one reason Mars's atmosphere is so thin today. The sun has been eroding it for billions of years. The absent magnetosphere also means the Martian surface is exposed to both solar energetic particles and galactic cosmic rays, high-energy protons and heavy nuclei originating from supernovae and other violent astrophysical processes beyond the solar system. Earth's magnetosphere and thick atmosphere combine to reduce surface radiation dose rates to approximately 0.01 millisieverts per day. On Mars, the surface dose rate is approximately 0.67 millisieverts per day, roughly 67 times higher. Over a 6-month stay, a human on Mars would accumulate a radiation dose approaching the career exposure limit set by most space agencies for astronauts. Over years, the cumulative effect would significantly increase cancer risk, potentially cause cataracts, and damage the central nervous system. But on the survival timescale, we are examining 60 to 90 seconds. The radiation dose is negligible. Even Mars's elevated flux would deliver less than 1 microsievert in 2 minutes. This is biologically insignificant. Radiation is Mars's slow-burning threat, dangerous for long-duration habitation but irrelevant to immediate unprotected exposure. Martian dust adds a final, subtler hazard. The soil of Mars contains perchlorate compounds, chlorine-based oxidizing chemicals, at concentrations of roughly 0.5 to 1% by weight, detected by the Phoenix lander in 2008 and confirmed by subsequent missions. Perchlorates are toxic to humans through multiple pathways. Ingested, they interfere with thyroid function by blocking iodine uptake. Inhaled as fine dust, and Martian dust particles are extremely fine, averaging roughly 3 micrometers in diameter, easily small enough to penetrate deep into the lungs. They would cause chemical irritation of the airways and long-term endocrine disruption. Mars's frequent dust storms, which can envelop the entire planet for months at a time and reduce visibility to near zero, would distribute these toxic particles across every exposed surface and into every unsealed crevice. Perchlorate toxicity operates on timescales of days to weeks. Like radiation, it is a long-duration threat invisible to the immediate survival calculation. But it illustrates a broader principle about Mars that sets it apart from every other planet we have examined. Mars possesses an entire ecosystem of lethal factors, each operating on a different timescale, each targeting a different physiological system. The near vacuum kills in seconds. The cold kills in minutes to hours. The radiation kills in months to years. The perchlorates kill in weeks to months. Mars does not have a single dominant survival threat. It has a hierarchy of threats, stacked by timescale, each one lethal in its own right, each one waiting its turn behind the faster killers. This hierarchy is what makes Mars uniquely cruel. On Mercury there is one fundamental problem: vacuum. Solve the vacuum and you have solved Mercury. On Venus there are two simultaneous fundamental problems: pressure and heat. You cannot solve either without solving both. On Mars, there are four fundamental problems: pressure, cold, radiation, and toxic chemistry. And solving any one of them leaves three more waiting. A pressurized habitat protects against the vacuum, but you still need heating against the cold, shielding against the radiation, and filtration against the perchlorate dust. Mars presents a layered gauntlet of lethality that would tax even the most advanced life support engineering. And through all of it, Mars continues looking habitable. The rovers keep sending postcards of rocky hillsides and dusty plains. The sky glows a familiar shade of amber at sunset. The terrain invites footprints. The illusion of hospitality is Mars's most dangerous quality. It encourages the imagination to underestimate the physics. It whispers that survival is just one engineering problem away, when in reality it is four interlocking engineering problems away, any one of which would be fatal if the others were solved. Those rovers have survived years on the Martian surface. Some have operated for more than a decade. They are machines. Some have operated for more than a decade. They are machines. They do not breathe. They do not require atmospheric pressure to keep their fluids liquid. They tolerate temperatures that would kill a human in hours and radiation doses that would cause cancer in months. They carry no blood that can boil, no cells that can freeze, no DNA that can be shattered by cosmic rays. A human being standing exactly where Perseverance is parked right now, without a suit, would be dead before the rover completed its next wheel rotation. The rover would continue photographing the landscape for years. The body beside it would freeze dry in the thin atmosphere, preserved by the cold and the desiccating vacuum for centuries or longer, a mummy on Mars, surrounded by the ghosts of ancient rivers. Your survival time on Mars: approximately 60 to 90 seconds. Loss of consciousness between 10 and 15 seconds. Cause of death: ebulism and anoxia from catastrophically insufficient atmospheric pressure. Contributing factors: extreme cold, toxic atmospheric composition, and radiation exposure, none of which get the chance to act before the atmospheric failure kills you first. 2 planets. 2 atmospheres at opposite extremes. Venus possesses approximately 93 times too much atmosphere and kills through compressive mechanical force in approximately 1 second. Mars possesses approximately 160 times too little atmosphere and kills through depressurization in approximately 60 to 90 seconds. Both fail the same fundamental test. Neither provides atmospheric pressure within the narrow range that human physiology requires. Both are lethal for the same root reason: the wrong amount of air, but they deliver that lethality through perfectly mirrored mechanisms. Venus crushes what Mars cannot contain. Venus incinerates what Mars freezes. Venus overwhelms what Mars cannot sustain. Earth sits between them. Not just geographically, Earth's orbit lies physically between Venus and Mars, but parametrically. Earth's atmosphere is heavier than Mars's and lighter than Venus's by factors that place it precisely in the narrow corridor where biological function is possible. This is not design, it is coincidence. The same volatile, rich planetesimals, the same outgassing processes, the same atmospheric chemistry operated on all 3 worlds. Venus ran away into thermal catastrophe. Mars lost its atmosphere to the solar wind. Earth held the middle ground. That middle ground is the reason you are alive. Carry that awareness forward. The inner solar system is finished. From here, We cross the asteroid belt into the realm of the giants' world, so massive they have no surfaces to die on, no ground to stand upon, no horizon to break your fall. The next two planets do not kill you where you arrive. They kill you as you descend. Every planet you have visited so far had one thing in common. There was ground. On Mercury, you stood on ancient cratered basalt baked by 4 billion years of unfiltered sunlight. On Venus, the ground was volcanic rock heated to the temperature of a self-cleaning oven. On Mars, iron oxide dust crunched underfoot like fine rust-coloured sand. The surface material varied, the geology differed, but in every case, there was a floor, a defined boundary where atmosphere ended and solid world began. You could, at least in principle, stand somewhere. Your feet would touch something. Gravity would hold you to a specific location on a specific surface, and whatever killed you would do so while you occupied a fixed point on a map. That concept ends here. Jupiter and Saturn are gas giants. They possess no solid surface, no bedrock, no regolith, no crust. There is no boundary where sky becomes ground, because the sky never stops. The atmosphere simply continues downward, growing denser and hotter and more compressed with depth, transitioning gradually from gas to liquid to states of matter so exotic they have no terrestrial analogue. If you were placed at the cloud tops of Jupiter or Saturn, you would not land, you would fall, and you would keep falling until the atmosphere became so dense it crushed you, so hot it incinerated what remained, and so deep that whatever was left of your body dissolved into the planet's interior like a sugar cube dropped into a warm ocean. The mechanism of death on the gas giants is not surface exposure, it is descent. The planet does not kill you at a place, it kills you across a distance. The dying is a journey measured in kilometres, with the environment deteriorating continuously as you plunge deeper into an abyss that has no floor. Jupiter is the Colossus, the dominant gravitational presence in the solar system after the Sun itself. Its diameter measures approximately 139,820 kilometers, roughly 11.2 times the diameter of Earth. Laid side by side, 11 Earths would barely span Jupiter's equator. Its volume could contain approximately 1,321 Earths. Its mass, approximately 1.898 times 10 to the 27th kilograms, exceeds the combined mass of every other planet, dwarf planet, moon, asteroid, and comet in the solar system. If you gathered everything orbiting the Sun that is not the Sun and weighed it, Jupiter would account for roughly 70% of the total. This mass produces a gravitational field that shapes the architecture of the entire solar system. Jupiter's gravity deflects comets, perturbs asteroids, and influences the orbital dynamics of every planet. It likely played a critical role in the early solar system by either scattering or accreting material that might otherwise have formed additional rocky worlds. Some astrophysicists argue that Jupiter's gravitational influence shielded the inner solar system from excessive cometary bombardment during the late heavy bombardment period roughly 4 billion years ago, reducing the frequency of sterilizing impacts on early Earth. Others argue the opposite, that Jupiter's gravity actually redirected material inward. The debate continues. What is not debated is Jupiter's gravitational dominance. It is the king of the planets by every quantitative measure, and stepping into its domain means entering a gravitational environment unlike anything the inner solar system can produce. Surface gravity on Jupiter, measured at the 1 bar pressure level, the altitude where atmospheric pressure equals 1 Earth atmosphere, used as the conventional reference point, since there is no surface, is approximately 24.79 meters per second squared. This is 2.53 times the gravitational acceleration on Earth's surface. The implications for your body are immediate and punishing. At 2.5 g, an 80 kilogram person would feel as though they weighed approximately 200 kilograms. Your skeleton, calibrated by evolution to bear loads at 1 g, would be forced to support 2.5 times its design weight. Standing upright would require enormous muscular effort. Walking would be exhausting within seconds. Your spine would compress under the load. Your knees and ankles would ache from the excess force transmitted through every joint. Blood, subject to the same increased gravitational pull, would pool in your lower extremities. Your heart, a muscular pump evolved to circulate blood against 1 g of resistance, would strain to maintain adequate blood pressure in your brain. At sustained g loads above approximately 3 to 4 g, most humans lose consciousness as cerebral blood flow drops below the threshold for neural function. At 2.5 g, you would remain conscious, but you would feel heavy, sluggish, and progressively impaired. Your cardiovascular system would work at its margin. None of this matters in the immediate survival calculus, because the atmosphere is unbreathable and the fall has already begun. But the elevated gravity shapes the timeline of your death by accelerating the descent. You fall faster on Jupiter. Terminal velocity, the speed at which aerodynamic drag balances gravitational acceleration, is determined by gravity, atmospheric density, and the drag characteristics of the falling object. In Jupiter's upper troposphere, where atmospheric density at the 1 bar level is relatively low and gravity is 2.5 times Earth's, terminal velocity for a human body would be substantially higher than on Earth. Estimates place it between roughly 150 and 250 meters per second, depending on altitude, body orientation, and local atmospheric conditions. On Earth, a skydiver in freefall reaches terminal velocity at approximately 53 meters per second in the spread eagle position. On Jupiter, you would fall 3 to 5 times faster. The atmosphere would rush past you with a violence that makes terrestrial freefall seem leisurely. The gas you are falling through is not air. Jupiter's atmosphere consists of approximately 89.8% molecular hydrogen and 10.2% helium by volume, with trace quantities of methane, ammonia, water vapor, hydrogen sulfide, and various hydrocarbons produced by photochemical reactions in the upper atmosphere. There is no molecular oxygen, not a trace, not a hint, not a single breathable molecule in the entire atmospheric column. Every breath you attempted would draw hydrogen and helium into lungs, evolved to extract oxygen from a nitrogen-oxygen mix. Helium is physiologically inert. It passes through lung membranes without interacting with blood chemistry. Hydrogen is similarly non-toxic at low pressures, but provides no metabolic utility. Neither gas can sustain consciousness. Hypoxia-oxygen starvation would begin with the first inhalation and progress rapidly. The timeline to unconsciousness follows the standard anoxia curve, 10 to 15 seconds from the last breath of oxygen-containing air. On Jupiter, you never take that last breath. You arrive in an oxygen-free environment and the clock starts immediately. Within 15 seconds, you lose consciousness. This is the same timeline as Mercury, Mars, and the vacuum of space. The mechanism is different on Mercury. There is no gas at all. On Jupiter, there is abundant gas, but none of it is usable, but the outcome is identical. The brain goes dark in roughly the same window regardless of whether it is starved by vacuum or drowned in the wrong gas. But on Mercury and Mars, unconsciousness was followed relatively quickly by death. On Jupiter, unconsciousness is followed by a prolonged descent during which the unconscious body is subjected to progressively worsening conditions. This is where Jupiter diverges from every world we have examined so far. The dying does not end when consciousness fails. It continues and it escalates. The cloud structure of Jupiter is layered into 3 principal decks. The uppermost layer, at altitudes near the 1 bar pressure level, consists of ammonia ice crystals. These crystals form the white and tan bands visible in telescope images. The temperature here is approximately negative 145 degrees Celsius. Below the ammonia deck lies a layer of ammonium hydrosulfide clouds at temperatures near negative 50 degrees Celsius and pressures of roughly 2 to 5 bars. Deeper still sits a water cloud layer at temperatures between 0 and 30 degrees Celsius and pressures of 5 to 10 bars. During the Galileo probe's descent in December 1995, instruments recorded conditions in the water cloud layer that were briefly, eerily Earth-like. For a narrow altitude band, perhaps a few dozen kilometers thick, the temperature and pressure fell within ranges compatible with liquid water, and theoretically, with biological survival. The Galileo data showed temperatures near room temperature and pressures comparable to a few meters below the ocean surface. Had you been conscious and breathing oxygen during this fleeting window, you would have experienced conditions more physically tolerable than anything else in the outer solar system. That window lasts seconds during a high-speed descent. You are unconscious when you pass through it, and it slams shut violently. Below the water cloud layer, the atmosphere transitions from familiar to alien. Temperature and pressure climb in tandem as you descend deeper into Jupiter's interior. At approximately 100 kilometers below the 1 bar level, a depth you would reach within a few minutes at terminal velocity pressure exceeds 100 bars. Temperature surpasses several hundred degrees Celsius. No biological tissue can remain intact under these conditions. The water in your body would become superheated liquid under the mounting pressure, preventing it from boiling but subjecting cellular structures to thermal destruction. Proteins would denature. Cell membranes would disintegrate. The distinction between living tissue and organic chemical soup would dissolve. As you fall further, the atmospheric hydrogen undergoes a gradual phase transition. At pressures of roughly 100,000 to 200,000 bars and temperatures of several thousand degrees Celsius, conditions that exist at approximately 1 to 2,000 kilometers below the cloud tops, molecular hydrogen is compressed so severely that it transitions into a liquid metallic state. In this phase, hydrogen atoms are packed closely enough that their electrons become delocalized, flowing freely between nuclei as they do in metals like copper or iron. Metallic hydrogen conducts electricity, generates magnetic fields, and behaves as a dense fluid with properties entirely unlike any substance found naturally on Earth's surface. This metallic hydrogen ocean, if it can be called an ocean, extends downward for tens of thousands of kilometers toward whatever core lies at Jupiter's center. The core itself remains poorly characterized. Data from the Juno spacecraft, which has been orbiting Jupiter since July 2016, suggests that the core is not a neat solid ball of rock and metal, as once assumed. Instead, Juno's gravitational measurements indicate a diffuse or dilute core, a region where heavy elements such as iron, silicon, and oxygen-bearing compounds are mixed gradually into the surrounding metallic hydrogen rather than concentrated in a distinct sphere. Core temperatures are estimated at approximately 20,000 to 36,000 degrees Celsius, with many current models centering near 24,000. Core pressures may reach tens of millions of bars. The conditions at Jupiter's center exceed those found at the surface of some low-mass stars. You do not reach the core. You do not reach the metallic hydrogen layer. The human body ceases to exist as a recognizable structure long before those depths are relevant. Here is the most probable timeline of destruction. You arrive at Jupiter's 1 bar level, ambient temperature, negative 145 degrees Celsius, pressure, 1 bar, atmosphere, unbreathable hydrogen-helium mix, gravity, 2.5 g. You are falling. Within 5 seconds, the cold begins damaging exposed tissue, frostbite on skin, crystallization of moisture in the airways. Within 10 to 15 seconds, cerebral anoxia causes unconsciousness. Your body is now in uncontrolled freefall through the ammonia cloud deck. You descend through the ammonium hydrosulfide layer within the next minute. Pressure climbs past 2 bars, 3 bars, 5 bars. Temperature rises but remains below zero. Your eardrums ruptured sometime around 2 to 3 bars, the pressure differential, exceeding what the tympanic membrane could sustain. Between 2 and 5 minutes, depending on fall rate and the local density profile of the atmosphere, pressure exceeds the structural tolerance of the human thorax. At roughly 5 to 10 bars, the compressive force on the chest wall overwhelms the ribcage. Ribs fracture inward. Lungs are crushed. The heart, compressed between the sternum and spine, ceases effective pumping. Major blood vessels rupture from the pressure gradient between internal and external environments. This is the moment of mechanical death, the point at which the body's structural integrity fails and organ function ceases irreversibly. The corpse continues to fall. Over the next minutes and hours, it descends into regions of increasing heat and pressure, at some point difficult to calculate precisely. Without detailed atmospheric modelling, the temperature exceeds the combustion threshold of organic tissue. Fats ignite, proteins char, bone calcines. The remains undergo thermal decomposition, breaking down into progressively simpler molecular fragments. Deeper still, even these fragments are absorbed into Jupiter's atmosphere, dispersed through currents of superheated hydrogen. Whatever molecules once constituted a human body become indistinguishable from the primordial gas that has been there since the solar system formed 4.5 billion years ago. There is no impact, no explosion, no definable moment of destruction. There is only descent continuous, relentless, deepening into an atmosphere that grows heavier, hotter, and more crushing with every passing second. The planet swallows you, and it takes its time digesting. The Galileo atmospheric probe, a titanium-shelled instrument package specifically engineered for Jupiter entry, survived to a depth where pressure reached approximately 23 bars, roughly 153 kilometers below the cloud tops. It transmitted data for 57.6 minutes before contact was lost. It was destroyed not by a single catastrophic event, but by the accumulated stress of mounting temperature and pressure. A machine built from advanced aerospace materials, backed by decades of engineering, designed specifically for this environment, lasted under an hour. A human body would last under 10 minutes. Your survival time on Jupiter, approximately 10 to 15 seconds of consciousness. Mechanical death from thoracic compression at approximately 2 to 5 minutes. Complete thermal and chemical dissolution over the following hours. Jupiter does not merely kill you, it absorbs you. Saturn appears, from a distance, like a gentler version of Jupiter, smaller, lighter, adorned with those spectacular rings that make it the most visually iconic planet in the solar system. Saturn's diameter measures approximately 116,460 kilometers, roughly 9.5 times Earth's. Its mass is about 95 times Earth's. These are enormous numbers, but they fall short of Jupiter's in every category. Jupiter is 318 Earth masses, Saturn is 95. Jupiter's diameter exceeds Saturn's by roughly 20%. Jupiter dominates, Saturn follows. This hierarchy of scale tempts the assumption that Saturn is proportionally less hostile, that it represents a diluted version of Jupiter's lethality. That assumption is wrong. Saturn is a different kind of killer. It does not overwhelm you with brute gravitational force. It draws the process out. The critical difference between Jupiter and Saturn begins with gravity. Saturn's surface gravity at the 1 bar pressure level is approximately 10.44 meters per second squared, only 6% higher than Earth's 9.8. This is extraordinary for a planet containing 95 Earth masses. The explanation lies in Saturn's density, or rather, its lack of density. Saturn is the least dense planet in the solar system. Its mean density is approximately 0.687 grams per cubic centimeter. Water has a density of 1 gram per cubic centimeter. Saturn is less dense than water. This remarkable buoyancy results from Saturn's composition overwhelmingly hydrogen and helium, the lightest elements in the universe puffed up by internal heat into a vast, low-density sphere. The mass is enormous, but spread across such a large volume that the gravitational acceleration at the cloud tops remains modest. For your body, this near-Earth gravity means the crushing sensation you would experience on Jupiter is absent. At 1.06 g, you would weigh 6% more than you do at home, barely noticeable. Your cardiovascular system would function normally. Your skeleton would bear its load without strain. Your muscles would operate within their designed parameters. Saturn's gravity does not assault your physiology the way Jupiter's does. It treats you gently. This gentleness is Saturn's cruelty, because it means you fall slowly. Terminal velocity through Saturn's upper atmosphere would be comparable to terminal velocity on Earth, roughly 50 to 70 meters per second, for a human body in freefall. This is less than half the fall rate on Jupiter. The descent takes longer. The pressure gradient builds more gradually. The killing stretch stretches. Saturn's atmospheric composition mirrors Jupiter's in its essentials. Approximately 96.3% molecular hydrogen, 3.25% helium, with traces of methane, ammonia, ethane, phosphine, and hydrogen sulfide, no oxygen. The atmosphere is entirely unbreathable by the same mechanism and for the same reasons as Jupiter's. Hypoxia begins immediately. Consciousness fails within 10 to 15 seconds. This timeline is constant across every oxygen-free environment we have examined, from Mercury's vacuum to Jupiter's hydrogen clouds to Saturn's upper troposphere. Hydrogen and helium fill the lungs without delivering anything the blood can use. The result is the same 15-second countdown to unconsciousness that began on Mercury and repeated on Mars. But the environment your unconscious body enters after those first 15 seconds is distinctly Saturnian. The cloud top temperature at Saturn's 1 bar level is approximately negative 178 degrees Celsius, about 33 degrees colder than Jupiter's corresponding altitude. This is deep cold. At negative 178 degrees, the thermal gradient between the environment and your body spans over 215 degrees. Exposed tissue would undergo rapid freeze damage. Moisture in the airways would crystallize. The lungs, already non-functional due to the unbreathable atmosphere, would suffer cold-induced tissue destruction. Frostbite would progress from the extremities inward during the first minute of descent, although you would be unconscious and unable to perceive it. The cold at Saturn's cloud tops is more severe than at Jupiter's because Saturn is farther from the Sun, roughly 9.5 astronomical units versus Jupiter's 5.2, and because Saturn, while generating significant internal heat, radiates less total thermal energy than Jupiter in its upper atmosphere. The upper troposphere is a frigid domain where ammonia ice crystals form the visible cloud deck, and temperatures sit well below the freezing point of any biologically relevant compound. But cold is not Saturn's signature weapon. Wind is. Saturn's atmospheric circulation produces some of the most extreme sustained wind velocities in the solar system. The equatorial jet stream on Saturn blows at approximately 1,800 kilometers per hour, 500 meters per second. For perspective, the speed of sound in Saturn's hydrogen-helium atmosphere is approximately 700 to 750 meters per second, depending on temperature and altitude. Saturn's equatorial winds reach roughly half to two-thirds the local speed of sound. These are not gusts. These are not sporadic storm events. These are permanent features of the atmospheric circulation. Maintained by Saturn's rapid rotation, the planet completes a full rotation in approximately 10 hours and 33 minutes, and by the release of internal heat that drives powerful convective cells. At 1,800 kilometers per hour, the dynamic pressure, the force exerted by moving gas on a stationary object, is enormous. Dynamic pressure scales with the square of velocity, meaning a doubling of wind speed quadruples the force. Winds at 1,800 kilometers per hour exert forces that would demolish any terrestrial structure designed for Earth conditions. The human body, falling through this wind field, would be subjected to lateral forces capable of tumbling, spinning, and deforming soft tissue. Windborne particles, ammonia ice crystals, ammonium hydrosulfide droplets would impact the body at velocities approaching those of high-caliber projectiles. The abrasive effect on exposed skin would be severe. Tissue would be eroded. Clothing would be stripped away. The combination of freezing cold and hypersonic particulate bombardment would reduce exposed tissue to a battered, frozen mass within the first minutes of descent. This wind assault occurs while you are unconscious, and while the pressure gradient is building. Saturn's lower gravity means the pressure increases more slowly with depth than on Jupiter. Where Jupiter's 2.5 G field drives atmospheric compression at a rate that reaches lethal pressures within 2 to 5 minutes, Saturn's 1 G field allows a more gradual accumulation. The The descent from the 1 bar level to the 5 bar level, the approximate threshold for thoracic crush, would take longer. Estimates suggest roughly 15 to 25 minutes, depending on atmospheric density profiles and fall dynamics. During those 15 to 25 minutes, your unconscious body is subjected to a sustained campaign of environmental violence. The cold freezes you, the winds batter you. Ammonia and hydrogen sulfide gas saturate your frozen clothing and tissue. Pressure builds at a pace slow enough to inflict damage incrementally, rather than catastrophically. Where Jupiter crushes you within minutes with overwhelming force, Saturn degrades you over a quarter of an hour with patient, relentless atmospheric persistence. Saturn's interior follows a similar structural progression to Jupiter's, though at a lower intensity. Below the cloud layers, the hydrogen-helium atmosphere transitions from gas to dense fluid to, eventually, metallic hydrogen at extreme depths. Saturn's metallic hydrogen layer is thought to be smaller and less conductive than Jupiter's, which contributes to Saturn's weaker magnetic field, roughly 1/20th the strength of Jupiter's. The core, estimated to contain approximately 15 to 20 Earth masses of heavy elements, sits at temperatures of roughly 12,000 degrees Celsius and pressures of several million bars. As with Jupiter, none of these deep interior conditions matter for your survival. The body fails long before the descent reaches exotic physics. The 15 to 25-minute descent to fatal pressure represents the outer boundary of the dying process. Within that window, the cold, the wind, and the asphyxiation have already rendered the body non-functional. Pressure at depth delivers the final structural failure: crushed ribs, collapsed lungs, ruptured vessels, but by the time it arrives, it is destroying a corpse that has been frozen, battered, and oxygen-starved for a quarter of an hour. Saturn's rings, the iconic feature that makes it the most photographed planet in the solar system, play no role in this analysis. The rings consist of countless particles of water ice and rocky debris ranging from dust grains to house-sized chunks, orbiting Saturn in a disk, roughly 280,000 kilometers in diameter, but only about 10 meters thick. They are spectacular. They are irrelevant to surface, or rather, atmospheric survival. The rings orbit at altitudes far above the 1 bar level, and a human arriving at cloud-top altitude would never interact with them. Your survival time on Saturn, approximately 10 to 15 seconds of consciousness, identical to Jupiter. Mechanical death from eventual thoracic compression at depth, occurring roughly 15 to 25 minutes into the descent. Contributing factors include severe cryogenic tissue damage, sustained high-velocity wind bombardment, and complete atmospheric asphyxiation. Saturn kills more slowly than Jupiter. It lacks Jupiter's crushing gravitational urgency. Instead, it substitutes duration. The atmosphere is a gauntlet rather than a guillotine, a prolonged passage through cold, wind, and mounting pressure that dismantles the body in stages rather than in one overwhelming instant. Two gas giants, no surfaces, no ground to touch, no floor to impact, no horizon to orient yourself against. On Jupiter, you fall into a gravity well so powerful that the atmosphere compresses you to death within minutes. On Saturn, you fall through a gravity field barely stronger than Earth's, but the atmosphere stretches the dying over a quarter of an hour, while wind and cold savage you the entire way down. Jupiter kills like a hydraulic press, fast, overwhelming, mechanical. Saturn kills like a blizzard with no ground, slow, relentless, patient, and certain. Both planets share one feature that separates them from every world in the inner solar system. The killing has no endpoint except depth. On Mercury, Venus, and Mars, you die at a location. You hit the ground. You arrive at the surface. There is a fixed point where the lethal conditions exist and where your body comes to rest. On Jupiter and Saturn, there is no such point. You never arrive. You never land. You fall until the atmosphere becomes your grave, and the grave descends with you as the pressure and heat increase without limit. The planet does not kill you somewhere. It kills you everywhere, all at once, on a gradient that extends from the cloud tops to the core. The outer solar system has two more worlds. They are smaller than Jupiter and Saturn, colder, composed of different materials, and they kill with a combination of mechanisms that the gas giants never quite achieve. Freezing temperatures so extreme they approach the theoretical floor of the solar system, atmospheric chemistry that poisons as it suffocates, and winds so fast they carry ice particles at speeds that shatter frozen flesh like glass. The ice giants are waiting. The solar system has one more trick, one final category of lethality that the inner planets and gas giants never quite delivered. Mercury killed through absence, Venus killed through crushing excess, Mars killed through deceptive inadequacy, Jupiter and Saturn killed through bottomless descent into compressing darkness. Each world presented a dominant mechanism of destruction: vacuum, pressure, atmospheric thinness, gravitational compression, and each mechanism operated according to its own physical logic. But every planet so far has left one weapon partially deployed: cold, real cold. Cold so extreme, it moves beyond the familiar territory of frostbite and hypothermia into a regime where the physics of freezing itself changes, where tissue does not gradually cool and slowly crystallize, but instead undergoes a phase. Transitions so rapid that cellular structures shatter from within like glass dropped on concrete. The ice giants occupy this regime. Uranus and Neptune are the coldest major worlds in the solar system, and they kill with a thermal brutality that none of the previous planets could match. But they do not rely on cold alone. They combine cryogenic temperatures with atmospheric chemistry that poisons and suffocates simultaneously. And in Neptune's case, with wind velocities so extreme they carry ice particles at speeds that exceed the structural tolerance of frozen human tissue. The ice giants do not merely kill you, they freeze you, choke you, and on the final planet shatter what remains. Uranus is the seventh planet from the Sun, orbiting at a mean distance of approximately 2.87 billion kilometers, 19.2 times Earth's orbital radius. At this distance, sunlight has been attenuated to roughly 1/370th of its intensity at Earth. If you hovered at Uranus's cloud tops and looked toward the Sun, you would see a bright point of light noticeably more luminous than any star, unmistakably the Sun but shrunken to a fraction of the disk you see from Earth. It would provide illumination roughly comparable to deep twilight. It would provide virtually no warmth. The solar energy arriving at Uranus per square meter of atmosphere is roughly equivalent to what a modest light bulb delivers. The planet exists in a state of permanent thermal deprivation, starved of the radiant energy that powers climate systems on the inner worlds. This thermal starvation is compounded by a peculiarity unique to Uranus. The planet generates almost no internal heat. Jupiter radiates approximately 1.67 times more energy than it receives from the Sun, a significant surplus driven by ongoing gravitational contraction and the slow settling of helium through its hydrogen-dominated interior. Saturn radiates approximately 2.5 times its solar input. Even Neptune, as we will see, produces substantial internal heat. Uranus, by contrast, radiates only about 1.06 times its solar input, functionally indistinguishable from thermal equilibrium. Whatever internal heat source Uranus once possessed has either been exhausted or is somehow trapped beneath insulating interior layers. The planet is thermally inert. It absorbs a trickle of sunlight and produces almost nothing from within. The result is the coldest planetary atmosphere in the solar system. Cloud top temperatures on Uranus reach approximately negative 224 degrees Celsius, 49 kelvins above absolute zero. This approaches the coldest temperatures measured anywhere in the planetary solar system outside of Pluto and the most distant trans-Neptunian objects. It is colder than the boiling point of liquid nitrogen, which sits at negative 196 degrees. It is colder than the boiling point of liquid oxygen at negative 183 degrees. At negative 224 degrees, both nitrogen and oxygen would exist as frozen solids. The air you are breathing right now, if transported to Uranus, would fall as crystalline snow. The thermal gap between this environment and a living human body is approximately 261 degrees Celsius. No previous planet has presented a gradient this severe at the altitude where an unprotected human would arrive. Mercury's night side approached negative 180 degrees, a gap of roughly 217 degrees from core body temperature. Mars at its coldest poles reaches negative 140 degrees, a gap of 177 degrees. Uranus exceeds both by margins that push the physics of heat transfer into a qualitatively different regime. At these temperatures, the rate of heat extraction from warm tissue into the surrounding environment is governed by the temperature differential and the thermal properties of the contact medium. Uranus's atmosphere at the 1 bar level has a density somewhat lower than Earth's sea level atmosphere, roughly comparable to Earth's atmosphere at an altitude of several kilometers. This density is sufficient to conduct heat away from exposed skin through direct molecular contact at a rate far faster than radiative cooling alone. The hydrogen-helium atmosphere, though less dense than Earth's nitrogen-oxygen mix, remains an effective convective medium, especially given that the temperature differential is over 15 times larger than anything experienced in Earth's coldest environments. The biological consequence is flash freezing. At negative 224 degrees, the water content of exposed tissue, which constitutes roughly 60 to 70% of skin, muscle, and connective tissue by mass, does not cool gradually the way it does during terrestrial hypothermia. Instead, the thermal gradient is so steep that the rate of cooling exceeds the rate at which intracellular water can migrate through cell membranes via osmosis. On Earth, slow freezing allows water to move out of cells and form ice crystals in the extracellular space, damaging, but potentially survivable at moderate levels. Flash freezing prevents this migration. Ice nucleates inside the cells themselves. Intracellular ice crystals expand as they form, puncturing organelles, shredding mitochondrial membranes, and rupturing the cell walls from within. The tissue does not slowly stiffen. It undergoes a catastrophic phase transition liquid biological matrix to solid crystalline mass within seconds. Exposed skin would reach tissue-destructive temperatures within approximately 2 to 4 seconds. The corneas of the eyes, which are thin, water-rich, and directly exposed to the atmosphere, would crystallize within 1 to 2 seconds, causing instantaneous and irreversible blindness. Mucous membranes lining the nasal passages, mouth, and upper airway would freeze on contact with inhaled gas, creating an ice-crusted barrier that would obstruct any attempt at breathing, even if the atmosphere contained oxygen. The trachea and bronchi, lined with moisture-producing epithelial cells, would suffer cryogenic damage throughout their length. Within 10 seconds, the freezing front would have penetrated several millimeters into all exposed tissue surfaces. Within 30 seconds, extremities, fingers, toes, earlobes, the tip of the nose would be frozen solid through their full thickness. Within 60 seconds, deeper tissues in the hands, feet, and face would reach cryogenic equilibrium with the environment. Core body temperature would decline on a slower but inexorable trajectory. The torso, insulated by clothing and subcutaneous fat, would retain warmth longer than the extremities. But the cardiovascular system, still functioning in the early seconds, would circulate blood that has been cooled in the peripheral vasculature. Each circuit of blood through the frozen extremities would return colder, progressively reducing core temperature. Once core temperature dropped below roughly 28 degrees Celsius, a decline of approximately 9 degrees from normal, the heart would become arrhythmic. Ventricular fibrillation would follow within minutes in a conscious, uninjured person. In a body already devastated by flash freezing of the airways and extremities, cardiac failure would arrive sooner. But the cold does not work alone on Uranus. The atmospheric composition introduces a second lethal mechanism that operates on the same timescale. Uranus's atmosphere consists of approximately 82.5% molecular hydrogen, 15.2% helium, and 2.3% methane, with trace quantities of hydrogen deuteride, ethane, acetylene, and hydrogen sulfide. The methane content is the critical differentiator. At 2.3% of the total atmospheric volume, Methane on Uranus is present at concentrations roughly 23,000 times higher than the approximately 1.8 parts per million found in Earth's atmosphere. Methane is the molecule responsible for Uranus's distinctive pale blue-green color. It absorbs red wavelengths of incoming sunlight and scatters blue-green light back toward the observer. It is also the molecule that makes Uranus's atmosphere chemically hostile, in a way that the gas giant's hydrogen-helium mixtures are not. Methane is classified as a simple asphyxiant. It is not toxic in the traditional sense. It does not poison metabolic pathways or damage tissues through chemical reactivity the way carbon monoxide or hydrogen cyanide does. Instead, methane kills by displacement. In an enclosed or ambient environment, methane molecules occupy volume that would otherwise contain breathable oxygen. At concentrations above roughly 15 to 20% in an Earth pressure atmosphere, methane reduces the partial pressure of oxygen below the threshold for consciousness. On Uranus, where the atmosphere contains zero oxygen and over 2% methane in a matrix of hydrogen and helium, every breath delivers a gas mixture that is triply non-sustaining. No oxygen to metabolize, hydrogen that is biologically inert, and methane that fills the lungs without contributing anything to gas exchange. The asphyxiation timeline on Uranus is identical to every other oxygen-free environment: 10 to 15 seconds to unconsciousness, 60 to 90 seconds to cardiovascular collapse from cerebral anoxia. This is the same clock that has ticked on Mercury, Mars, Jupiter, and Saturn. The brain does not care whether it is being starved by vacuum, drowned in carbon dioxide, or smothered in hydrogen methane. It runs out of oxygen and fails. What makes Uranus unique is that the cold and the asphyxiation arrive simultaneously and operate on nearly identical timescales. On Mercury and Mars, vacuum killed before cold could finish the job. On Jupiter and Saturn, anoxia ended consciousness before the mounting pressure completed thoracic compression. In each previous case, one lethal factor outpaced the other, creating a hierarchy where the fastest killer determined the survival time and the slower threat became secondary. On Uranus, there is no clear hierarchy. Flash freezing of exposed tissue is devastating within the first 5 to 10 seconds, the same window in which anoxia is shutting down the brain. The two mechanisms are co-dominant, attacking the body in parallel with roughly equal urgency. Neither clearly outpaces the other. Both contribute to the rapid collapse of biological function. Your survival time on Uranus: approximately 10 to 15 seconds of consciousness, with complete biological death from combined flash freezing and anoxia occurring within approximately 20 to 40 seconds. The body would reach thermal equilibrium with the surrounding atmosphere within minutes, a frozen mass at negative 224 degrees, drifting through Uranus's cloud layers, structurally intact at the macroscopic level but destroyed at the cellular level. Every cell ruptured from within by intracellular ice, every protein denatured by thermal shock, every membrane shattered. Uranus would preserve the shape of a human body while annihilating everything that made it alive. Uranus's gravity, approximately 8.87 meters per second squared, nearly identical to Earth's, would slowly draw the frozen remains downward into deeper atmospheric layers. Over hours and days, the body would descend through regions of increasing pressure and temperature. At some depth, the temperature would rise above the melting point of water ice, and the frozen tissue would begin to thaw, though by then, the cellular destruction would be absolute. Deeper still, the remains would be compressed and heated until thermal decomposition reduced them to molecular fragments dispersed through Uranus's interior. The process would be slower than on Jupiter, gentler than on Saturn, and absolutely irreversible. Neptune is the final planet, the outermost world in the solar system. It orbits at a mean distance of approximately 4.5 billion kilometers from the Sun, 30.07 astronomical units. At this distance, sunlight is approximately 900 times dimmer than at Earth. The Sun from Neptune would appear as a brilliant star, unmistakably brighter than anything else in the sky, but reduced to a point source so small that its disk would be barely resolvable to the naked eye. The solar energy reaching Neptune is so feeble that it contributes almost nothing to the planet's atmospheric dynamics. Neptune runs on internal heat, and it runs hard. Unlike Uranus, which sits in thermodynamic torpor, Neptune radiates approximately 2.61 times more energy than it receives from the Sun. This vigorous internal heat output, believed to originate from ongoing gravitational contraction, compositional differentiation, or some combination of both, drives Neptune's atmosphere into a state of violent dynamism that no other planet in the solar system can match. Neptune is the windiest world ever measured by human instruments, and wind on Neptune is a weapon of a kind that has not appeared anywhere else on this journey. Neptune's diameter is approximately 49,244 kilometers, slightly smaller than Uranus, but its mass, at roughly 17.15 Earth masses, exceeds Uranus's by nearly 3 Earth masses. This higher mass, packed into a slightly smaller volume, gives Neptune a mean density of approximately 1.638 grams per cubic centimeter, making it the densest of the 4 giant planets. Surface gravity at the 1 bar pressure level measures approximately 11.15 meters per second squared, roughly 14% stronger than Earth's. You would notice the extra weight on Neptune. It would feel like carrying a moderately heavy backpack, but it would not impair your movement or cardiovascular function in any meaningful way during the seconds you had left. The atmospheric composition closely mirrors Uranus. Approximately 80% molecular hydrogen, 19% helium, and roughly 1.5% methane, with traces of hydrogen deuteride, ethane, and hydrogen sulfide. The methane concentration is slightly lower than Uranus's 2.3%, but the difference is marginal. The atmosphere is equally unbreathable, equally devoid of oxygen, and methane remains present in concentrations far above any terrestrial norm. Asphyxiation follows the standard timeline: unconsciousness in 10 to 15 seconds, cardiovascular collapse within 60 to 90 seconds. The cloud top temperature on Neptune is approximately negative 214 degrees Celsius, roughly 10 degrees warmer than Uranus. This seems paradoxical. Neptune is 1.5 billion kilometers farther from the Sun than Uranus. It should be colder. The explanation is the internal heat. Neptune's vigorous energy output warms the atmosphere from below, producing cloud top temperatures slightly above what solar heating alone would yield. The difference 10 degrees is real but barely significant for survival purposes. At negative 214 degrees, the thermal gradient between the environment and the human body is approximately 251 degrees. Flash freezing proceeds on essentially the same timeline as on Uranus. Exposed tissue destroyed within seconds. Extremities frozen solid within 30 seconds. Core temperature in rapid decline. If Neptune merely replicated Uranus's conditions with a 10-degree offset, it would be a footnote, a slightly warmer copy of the same cryogenic death. But Neptune is not a copy. Neptune adds a dimension of violence that Uranus does not possess. Neptune has wind. Measured wind speeds on Neptune reach approximately 2,100 kilometers per hour. This figure, recorded by the Voyager 2 spacecraft during its August 1989 flyby, the only spacecraft visit to Neptune in history, represents the highest sustained atmospheric wind velocity ever measured on any planet. In the solar system, Saturn's equatorial jet reaches approximately 1,800 kilometers per hour. Neptune exceeds this by roughly 17%. Jupiter's peak winds, at approximately 360 kilometers per hour in the jet streams flanking the Great Red Spot, are dwarfed by comparison. 2,100 kilometers per hour demands contextualization because the number is so far beyond terrestrial experience that intuition fails entirely. The most powerful tornado ever recorded on Earth, the Bridge Creek, Oklahoma tornado of May 1999, produced winds estimated at approximately 484 kilometers per hour. Neptune's winds are more than 4 times faster. The fastest wind gust ever measured on Earth's surface at Barrow Island, Australia, during Tropical Cyclone Olivia in 1996, reached approximately 408 kilometers per hour. Neptune exceeds this by a factor of 5. The muzzle velocity of a 9mm pistol round is approximately 1,300 kilometers per hour. Neptune's winds move roughly 60% faster than a bullet fired from a handgun. The speed of sound in Neptune's hydrogen-helium atmosphere is approximately 550 to 600 meters per second. Depending on local temperature and composition, roughly 1,980 to 2,160 kilometers per hour. Neptune's measured peak winds of 2,100 kilometers per hour therefore approach the local speed of sound. These are transonic winds, atmospheric flows operating at the boundary between subsonic and supersonic regimes. At certain altitudes and latitudes, the winds may intermittently exceed the local sound speed, producing shock waves within the atmospheric flow itself. The force exerted by gas moving at these velocities is proportional to the gas density and to the square of the velocity. Neptune's atmosphere at the 1 bar level is denser than Uranus's at the equivalent altitude, owing to Neptune's stronger gravity, compressing the atmospheric column more effectively. The dynamic pressure, the kinetic energy per unit volume of the moving gas at 2,100 kilometers per hour in Neptune's atmosphere vastly exceeds anything a human body could withstand. The force would not merely push you, it would deform you. At these wind speeds, the human body is not an obstacle. It is a soft, destructible object in the path of a fluid, moving with the kinetic energy density of an industrial blast. But wind alone is not what makes Neptune uniquely lethal. Wind-carrying material is what transforms it into something worse. Neptune's atmosphere contains ice crystals, methane ice, ammonia ice, and possibly water ice particles entrained in the atmospheric flow. These particles, though individually microscopic, are accelerated by the wind to velocities approaching 2,100 kilometers per hour. At these speeds, even tiny ice crystals carry kinetic energy comparable to high-velocity projectiles. The flux of millions of such particles per second across the cross-sectional area of a human body constitutes a sustained blast of cryogenic shrapnel. Now consider what those particles strike. The body is not at room temperature. It has been exposed to negative 214 degrees for seconds. The outer tissue layers are already frozen, and frozen biological tissue has radically different mechanical properties than living tissue. Living skin is elastic, pliable, and capable of absorbing impact energy through deformation. Frozen skin is rigid, brittle, and prone to fracturing under mechanical stress precisely the way ice behaves when struck. A frozen finger snaps rather than bends. Frozen muscle shatters rather than tears. The body that Neptune's winds assault is not a resilient biological structure. It is a brittle, ice-filled shell, and the winds carry enough force and abrasive material to fragment that shell. The combined effect is unlike anything on any other planet. Cold freezes the body into rigidity within seconds. Wind-carrying ice particles strikes the frozen surface at transonic velocities. The frozen tissue fractures, fragments, and erodes under the sustained kinetic bombardment. Neptune does not merely kill you, it freezes you solid, then sandblasts the frozen remains into pieces. It is the only planet in the solar system where the mechanical destruction of the body after death is as dramatic as the killing itself. Your survival time on Neptune: approximately 10 to 15 seconds of consciousness, the same anoxia timeline as every oxygen-free world. Biological death within 20 to 40 seconds from combined flash freezing and asphyxiation, identical to Uranus. Physical destruction of the frozen remains by sustained wind forces over the following minutes. Neptune kills on the same schedule as Uranus, but continues the assault long after death, dismantling the evidence with a thoroughness no other planet achieves. Voyager 2, during its 1989 flyby, observed the Great Dark Spot, an anticyclonic storm system approximately the size of Earth, with winds at its margins exceeding 2,000 kilometers per hour. It also observed smaller storm features, atmospheric bands, and turbulent shear zones where adjacent layers moved at wildly different velocities. When the Hubble Space Telescope revisited Neptune in 1994, the Great Dark Spot had vanished, replaced by new storm systems in different locations. Neptune's atmosphere is not just violent, it is chaotically variable, reshuffling its storm systems on timescales of years. The violence is constant. The geography of violence shifts. The ledger is complete. 8 planets, 8 environments, 7 signatures of destruction. Mercury, vacuum and thermal extremes. No atmosphere, ebulism and anoxia within 15 seconds. Death in 60 to 90 seconds. Venus, atmospheric pressure and temperature. 92 atmospheres of carbon dioxide at 465 degrees. Death in approximately 1 second. Earth, full atmospheric support. Indefinite survival. The sole entry with no lethal constraint. Mars, near vacuum atmosphere with cold and radiation. Ebulism and anoxia within 15 seconds. Death in 60 to 90 seconds. Jupiter, unbreathable hydrogen-helium atmosphere with extreme gravity and bottomless descent. Consciousness for 10 to 15 seconds. Mechanical death from pressure at depth in 2 to 5 minutes. Saturn, unbreathable atmosphere with extreme cold, transonic wind, and slow pressure accumulation. Consciousness for 10 to 15 seconds. Mechanical death at depth in 15 to 25 minutes. Uranus, cryogenic cold and chemical asphyxiation. Consciousness for 10 to 15 seconds. Death in 20 to 40 seconds. Neptune, cryogenic cold, asphyxiation, and hypersonic wind destruction. Consciousness for 10 to 15 seconds. Death in 20 to 40 seconds, followed by physical fragmentation. 7 worlds. 7 ways to die. 1 world where the dying does not happen. The numbers reveal something that no amount of descriptive language can capture as precisely. The survival window on Earth is not the product of one favourable parameter. It is the product of all 5 critical parameters: pressure, oxygen, temperature, radiation shielding, and gravity aligning simultaneously within their respective survivable ranges. No other planet achieves this with even 1 parameter. Venus matches Earth's gravity almost exactly, but fails catastrophically on pressure and temperature. Mars provides a visible sky and geological features carved by ancient water, but delivers pressure 160 times too low. Jupiter's atmosphere passes through a pressure and temperature band briefly compatible with liquid water during descent, but the atmosphere is unbreathable, and the band lasts seconds before conditions deteriorate beyond any biological tolerance. Each planet offers a partial overlap, 1 parameter, sometimes 2, that falls within the human survival range, while the remaining parameters deviate so far from biological tolerance that the partial match is rendered meaningless. Earth provides every parameter at once. Pressure, 101.3 kilopascals, within the range that keeps blood liquid and lungs functional. Oxygen, 21% at sea level, within the range that sustains consciousness and metabolism. Temperature, global average of 15 degrees Celsius, within the range that allows thermoregulation. Radiation, magnetosphere and ozone layer reducing surface doses to biologically manageable levels. Gravity, 9.8 meters per second squared, the value around which every structural and cardiovascular system in the human body is engineered. 5 parameters, 5 windows, all open simultaneously, all the time. The probability of this alignment is not calculable in any rigorous sense, because we have only 1 example, 1 solar system with 1 habitable world. We cannot compute the frequency of Earth-like parameter alignment from a sample size of 1, but we can observe that among the 8 major bodies orbiting our star, formed from the same primordial material, shaped by the same gravitational and thermodynamic processes, only 1 achieved the alignment. The other 7 failed. Some failed narrowly. Mars may have been habitable billions of years ago before its atmosphere was stripped away. Some failed catastrophically. Venus underwent a runaway greenhouse effect that transformed a potentially temperate world into the hottest surface in the inner solar system. The history of the solar system is a history of atmospheric and thermal evolution, in which 7 out of 8 outcomes were lethal, and only 1, by a combination of distance, mass, magnetic field strength, atmospheric composition, and geological activity, threaded the needle. There is a temptation, arriving at the end of this journey, to frame the conclusion emotionally, to speak of Earth's beauty, to invoke gratitude for oceans and forests and breathable air, to urge reverence for the fragile balance that sustains us. That temptation should be resisted, not because the emotion is wrong, but because it is imprecise. The balance is not fragile in the poetic sense. It is fragile in the engineering sense. It is a system operating within tolerances, and the tolerances are narrow, and the consequences of exceeding them are not metaphorical, they are physical. They are measured in seconds. Every planet in this solar system demonstrated the same underlying lesson through different mechanisms. The vacuum of Mercury, the furnace of Venus, the deceptive thinness of Mars, the crushing depths of Jupiter, the patient winds of Saturn, the cryogenic stillness of Uranus, the frozen violence of Neptune. Each world presented a unique combination of physical parameters, and each combination was lethal, and the lethality was not a matter of degree but of kind. These planets do not make survival difficult. They make survival impossible, not improbable, not challenging, physically, mechanically, thermodynamically impossible for an unprotected human body. The lesson is not that space is dangerous. The lesson is that habitability is extraordinary. The default state of a planetary surface in this solar system is death. Instant, overwhelming, physics-driven death. Earth is the exception. Earth is the anomaly. Earth is the one world where the parameters converged and held stable for long enough that chemistry became biology, and biology became you. Survival in the solar system is not about bravery. It is not about technology or determination or the human spirit. Those qualities matter on Earth, where the parameters support life and the challenge is navigating within them. Beyond Earth, those qualities are irrelevant. No amount of courage changes the boiling point of blood in a vacuum. No quantity of ingenuity prevents thoracic collapse at 92 atmospheres. No measure of determination keeps neurons firing without oxygen. Survival in the solar system is about physics, and the physics is unambiguous. You can survive on exactly one planet. You are living your life on it right now.